Good morning, everyone. I'm very proud to have the opportunity of having a talk at the meeting. First, please let me express my great thanks to Professor Lee and Professor Wu for organizing such a meeting. Today, my talk is about a quasi-interpolation scheme for periodic data based on multiquadric trigonometric B-spline. This is a joint work with my supervisor, Professor Wu. My talk mainly consists of 4 parts. First, I shall give a short introduction of our motivation. And the second part is the main results of our talk. The third part is some numerical examples to demonstrate the efficiency of our quasi-interpolation schemes. Finally, I shall give some conclusion and discussion. Okay, now let's begin with our first part. As we know, periodic data exists widely in practical applications. For example, reconstructing any simply closed curves or surfaces, such as this, constructing active contours. Oh, sorry, the red circle is missing. Constructing the active contours, such as boundary detection and image processing and geometrical modeling in CAD and CHD, fitting data collected at the Earth's surfaces, such as the geodetic data and the meteorological data, the seismic data, and so on. Finally, some time series analysis. For periodic data, usually interpolation is all common to fit data. There are famous interpolation schemes. For example, the spline interpolation, the trigonometric spline interpolation, and the radial basic function interpolation, and so on. However, as we know, interpolation has to solve a linear system of equations. This may make the scheme time-consuming and unstable when the assembly data contains some noise. Moreover, when the interpolation, the collocation point, the number of the collocation point is large, interpolation may yield a yield-conditioned coefficient matrix. To overcome these drawbacks, some people use quasi-interpolation instead of interpolation in some cases. Quasi-interpolation has been studied extensively in the literature. More details can be referred to this person's papers and works. Given the data xj, fxj, j ranging from 1 to n, and a basis psi jx, quasi-interpolation usually takes this form. Some examples of quasi-interpolation are that when the basis psi jx are the Bernstein's polynomials. This is the famous Bernstein approximation in approximation theory and CHD and so on. Another famous interpolation scheme is the Schoenberg model. Some examples of Schoenberg model are B-spline quasi-interpolation and Shannon sampling series. Finally, a very famous quasi-interpolation scheme is MQ quasi-interpolation. The basis is the MQ functions. Now I shall give some short introduction of MQ quasi-interpolation. Since Hardy introduced the MQ function for x, where here C is a positive shape parameter, it controls the shape of x. Bowman studied convergence of MQ quasi-interpolation on uniformly north sequence over the whole real line. However, as we know, in applied mathematics, usually the sampling data may be scattered, and the approximate usually defined on a boundary interval. Thus, to make MQ quasi-interpolation more applicable, Beach and Paul first construct MQ quasi-interpolation for scattered centers on a bounded interval. Wu and Shabak improved Beach and Paul's results further and studied the shape preserving properties of MQ quasi-interpolation. B-splines even applied MQ quasi-interpolation in the same design of Lord of the Rings 3. He used MQ quasi-interpolation to design such a monster. Some other people also apply MQ quasi-interpolation in numerical solution of PDEs. MQ quasi-interpolation, now let's see some the advantages of MQ quasi-interpolation. Since it gives a solution directly, it takes short CPU time for computation. Moreover, it can filter the noise contained in the data. And it can preserve shapes of the approximate, which is very usually required in geometric modeling such as CAD and CAM. Moreover, it can approximate high-order derivatives and is much stable than high-order derivative difference. This has been proved by Professor Wu in 2009 and 2010 in these two papers. However, MQ quasi-interpolation is not very suited for the periodic data. This is the main reason is that the kernel, the MQ function varifying x is not a periodic function. That if one has to use MQ quasi-interpolation for periodic data, they have to do periodic extensions. This may require many boundary conditions and yield unwanted high-order discontinuous points at the boundary, since one can't do infinite smooth extension. Moreover, as we know, for periodic problems, there is no concept of boundary. Thus, to fit periodic data, it's better to use a quasi-interpolant with periodic kernel. Based on such as Luke, Schumacher, and Stanley constructed trigonometric B-spline quasi-interpolation. For the second case, the trigonometric B-spline quasi-interpolation takes this form. From the trigonometric B-spline quasi-interpolation, we can find that since its kernel, the sine function is periodic, that is more suitable for periodic data. Moreover, the approximation, it gives an optimal approximation order with respect to the order of the trigonometric B-spline. As we know, for the second case, the second order trigonometric B-spline quasi-interpolation gives the approximation order of 2. However, since the kernel of the trigonometric B-spline quasi-interpolation, the order of smoothness is finite. This implies that in some cases, if we want to use this quasi-interpolation to approximate high-order derivatives, we have to use high-order trigonometric B-spline quasi-interpolation. It will make the scheme unstable, since, as we know, high-order trigonometric B-spline involve computation of high-order divided differences. Then, based on the above discussion, a question arises: can we construct a quasi-interpolant that covers together the field properties of both MQ and trigonometric B-spline quasi-interpolants? Of course, the answer is yes. Now let's show how to construct such a quasi-interpolant. This is the second part of our talk. The construction mainly consists of 3 steps. As the first step, we construct a periodic kernel. Here, in parallel with the MQ function, we call it MQ trigonometric function. This function is constructed based on trigonometric kernel and the MQ kernel is constructed as this form. From this form, we can see that the kernel phi x places both periodicity and smoothness. Then with this kernel, we can construct the multiquadric trigonometric B-spline in this form. Here, the nodes xj is are pi periodic. Finally, with this trigonometric B-splines, we can construct it or quasi-interpolate in this form. Now, let's give the error estimates of the quasi-interpolate. This is the error estimate. Let fx be a C2 continuous function with period r pi denoted by h, the density of the center xj. Here h, that's h. Let C be an h-dependent shape parameter. Then the error of the quasi-interpolate scheme, QMTRF is given as this form. From this error estimate, we can see that the shape parameter C is very important for the approximation order of the quasi-interpolate. Rather now, let's see how to give the choice of the shape parameter C. That's the choice of the shape parameter. From the error estimate, we can see that if we choose C satisfies the inequalities, then this error becomes this form. Now let's compare with the trigonometric, the second order trigonometric approximation order. We can see that it gives the same approximation order as the trigonometric B-spline quasi-interpolation. Moreover, as we know, the second order trigonometric B-spline is a special case C is 0. Thus, our quasi-interpolates gives more choice of the shape parameter. The shape parameter can range from 0 to O, h minus h divide log h square. Though as we C can range from this interval, however, the influence of the shape parameter, the choice of the shape parameter will influence the quasi-interpolate greatly. That's to show the influence of the shape parameter. Let's give three examples. The first example is about approximating the function fx with our quasi-interpolate with different shape parameters. And the second example is approximating the first order derivative of fx with our quasi-interpolate. The last example is approximating the second order derivative of fx with our quasi-interpolate. This is the first order derivative, this is the second order derivative. Now let's see the first figure. In the figure, this to demonstrate the efficiency, the picture efficiently, we choose the center n equals 16, a small number of n. In the picture, the red line equal to the corresponds to the case C is 0, while the green, the magnetic, and the Cn correspond to different choice of the shape parameter. Here the blue curve denotes the function fx. From the curve, we can see that the red line here, the red line correspond to the red curve correspond to the case C is 0, gives the best approximation to the function, while the Cn curve, this curve, gives the worst approximation to the function. This implies that if one only wants to approximate the function, then the best choice of the shape parameter is C is 0. However, just as I have said that the second, in this case, all co-interpolants become the second order trigonometric B-spline co-interpolation. However, the second order trigonometric B-spline co-interpolation, as we know, its smallest order is 0. Thus, it can counter-approximate its first order derivative. This figure shows the approximation of our co-interpolant with the first order derivative, this function. In the figure, we can see that there is very oscillation for the Z curve. This implies that if we want to approximate the first order derivative, the red line corresponds to C0 is the worst, gives the worst approximation, while the CN curve gives the best, since these three curves both have some oscillations. Finally, as the last example, we see the approximating of our co-interpolants with the second order derivative. This is the second order derivative of the function. Then we can see that the red line, the red curve oscillated very large and frequently. And the green curve and the magnetic curve also oscillated frequently. From this figure, we can see that the CN curve gives the best approximation to the second order derivative. From these three figures, we can see that although we can choose different shape parameter for approximating the function, and it provides the same approximation order, the approximation order is order 2. However, from this figure, we can see that for large values of the shape parameter, our co-interpolant will yield smoother co-interpolation with better approximation to derivatives, as we see in the second figure and the third figure. Here it is equal to the largest shape parameter gives, here it gives the best approximation to the first order derivative, while in this figure it gives the best approximation to the second order derivative. Yet more accurate co-interpolants to yield better approximation to derivative. However, while smaller one, as we see in the first figure, will yield more accurate co-interpolants for the function. As we see, this first figure is about approximation for the function with worse smoothness, as we see in the third and in the second and the third picture. It can't approximate its derivative with worse smoothness. This implies that if one needs to the co-interpolation to approximate high order derivatives well, while still providing the same approximation order for the function, then one has to choose a large shape parameter. Now let's compare our co-interpolation with trigonometric B-spline co-interpolation. From the above discussion, we can see that our co-interpolation includes trigonometric B-spline co-interpolation as a special case C is 0. Moreover, it provides more choice of the shape parameter C can be chosen in this interval. Finally, more importantly, it also plays the same approximation order as the second order trigonometric B-spline. This is the approximation order of the second order trigonometric B-spline. Finally, let's compare our co-interpolation with the periodical MQ co-interpolation. This figure shows the approximation of the second order derivative of a periodic function that's approximating this function with our co-interpolant and the periodical MQ co-interpolation. The red curve is the figure of periodical MQ co-interpolation, while the green is our co-interpolation. From the figure, we can see that at these two boundaries, the periodical co-interpolation can't approximate the second order derivative at these two boundaries. We can see that it decreases rapidly. This also demonstrates that periodical MQ co-interpolation can't approximate the second order derivative at the boundaries. We can see this in turn also verifies that periodical interpolations can yield high order discontinuous points at the boundary, yield the second order discontinuous points at these two boundaries, as we see. Finally, as the third part of our talk, I shall give some numerical results. This is about approximating the function with our co-interpolant and the different densities. Here is the post-error estimate. From this post-error estimate, we can see that our co-interpolants give approximation. The least is about 2.1, which while the priority is 2. As the second example, we show approximating the first order derivative with approximating the first order derivative with different density center. From this post-error estimate, we can see that its approximation order is about 1.5, which is better than its counterpart, the prior counterpart 1. Finally, as the last example, I should is about approximating the second order derivative of the function with our co-interpolant. From this post-error estimate, we can see that our co-interpolant can even approximate the second order derivative with approximation order 1.2. This demonstrates that our co-interpolants give better approximation for both the function and its derivative, which is better than trigonometric B-spline co-interpolation, since the final order derivative is the order of smoothness is finite. It has to use high order derivative differences. Finally, let's give some conclusion and discussions of our talk. In our talk, we mainly talk about how to construct a periodic co-interpolant for periodic data, and discussion of the choice and influence of the shape parameter are given in our talk. From the discussion, we can see that we can choose a proper shape parameter such that the co-interpolant provides fair approximations to the function to high order derivative without losing the approximation order for approximating the function. This implies that our coordinate plane can not only approximation function well, it also can approximate high-order derivatives. Finally, we compare our coordinate planes with our coordinate plane with MQ and trigonometric B-spline coordinate plane. From this, through numerical example, from this example, we can see that our coordinate planes can couple together the the field properties of MQ coordinate plane and trigonometric B-spline coordinate plane. This implies that our coordinate plane is better for periodic data than both two coordinate plane schemes. Okay, that's maybe time maybe over. That's all our talk. Thanks.